this talk is going to be about using GHC as an API to compile a language that's kind of like Haskell, but not quite. And I am fortunate enough that last year Morten's keynote at Haskell Implementor's workshop kind of gave the background to this, so I can skip a lot of it by just referring to the keynote last year. But for us here, what's important, I guess, is that Standard Chartered is a bank and it uses Haskell in computations involving financial modeling and analysis. And all that code is implemented in a lot of Haskell because like Mu is a Haskell dialect. So if you add it all up, it's like 3/4 Haskell. And that's usually the number that we would throw out for advocacy purposes. But what's important for us now is that we have 4.5 million lines of code of Mu. So anything we do will have, yeah.
How much of that is generated?
I don't know. I mean, this is slog count being run like last week. Just so I can put some numbers there. I mean,
That's a lot.
Yeah, which one? The 4.5 million?
Yeah.
I mean, okay, so, but even if the generated stuff is not going to be that much, like we have some lens stuff, but yeah. So order of magnitude, this is real. These numbers are real. So 4.5 million lines of code in Mu, and this is like anything we do, we'll have to keep kind of working with this large existing code base. So the two main characters of this story are going to be Cortex and Mu. These are the names, like in-house names of proprietary stuff, so you don't care, but I only mention these because I need some way of referring to them. So Cortex is the runtime that all this financial analytics is built on top of. The two main features of it that it provides is language interoperability through an admin system, so you can write C++, Java, C#, Haskell functions, and they all get exposed via this unified API to your scripting language. And the other thing is code mobility and cross-platform code mobility. So at the bottom of it, there's a bytecode interpreter, and basically you can send your closure from one machine on one architecture to another machine on another architecture, run it there, serialize the result back, and this all works. And so what is the scripting language that you use to drive all this? That is Mu, which is our in-house dialect of Haskell. And it has lots of small differences to Haskell. And I think the one that everyone knows about is that it's strict, but we're going to get to that later. But for now, I want to mention that the sources of these script programs are not necessarily just files. They can be retrieved over a network, or they can be stored in a database or whatever. This is going to be important later on when we get to using GHC to compile it. And so the Mu compiler today is based on Haskell source extensions for parsing, and then everything else is fully in-house developed. So there's a scope and type checker tied together. And then there's desugaring into our exp, which is basically our core. And then there's a series of optimizations and lowerings in exp. And then we finally get to exp that is simple enough that we can generate bytecode from it. So bytecode that runs on this Cortex runtime. And originally, the Mu compiler written in 2009, 2010 by Leonard. And we would like to update it. And we would like to migrate to something that will be easier to maintain than the full stack ourselves. So the project that we have started is to use GHC as the front end, and then hopefully get lots of language features for free, hopefully decrease the maintenance cost, and hopefully get performance improvements out of it as well. So the current status of this is that we've put about 2 man-years of work into it, and we're already at the point where we can compile pre-existing real Mu programs. So Mu programs that were written for the old compiler, and we can compile them with the new compiler, and the result runs and behaves correctly, and not hello world, but like complicated GUI apps. So the rest of this talk is basically just going to be about the technical details of Mu and Cortex. Like, why is this interesting? Because you might think that, okay, well, it's like, okay, we can replace one Haskell compiler with another, that like we changed the make file a couple of places to invoke GHC and we're done. That's not a talk. So I'm trying to convince you that it's actually more interesting because there are some details that are very different to what GHC assumes. So let's talk about Mu first. So the baseline of Mu is Haskell 98 with some changes. So we have non-lazy evaluation in the same sense that GHC has like non-strict evaluation. So it's not quite strict, but because there are a couple of places where you can be lazy. Like imagine, like you want from maybe error or something to work, right? So there are some, and I'll get to how that's done. Recursion is disallowed by default, but of course you can enable, like you can enable a language extension flag to enable recursion. Polymorphic recursion is not supported. We will see why. Local definitions are not generalized, meaning that if you don't put a type signature on your where or let bound definition, it's not going to be polymorphic. And then on top of Haskell 98, we have multi-parameter type classes with functional dependencies, and that's about the limit of what Mu does. But there are other things that are different. So we have a primitive string type. Car doesn't exist at all. The notation bracket A, bracket actually stands for arrays instead of lists. And then we get to the more interesting things. So actually signature sections, I have a lightning talk about that, but I think that's still on, like there's a reason it's on the less interesting stuff slide. That's just syntax for doing a type signature in the middle of a term, or like if you have like some point-free expression and you want to put a type signature in the middle, then it's syntax for that. So then more interesting things. So you can define instances for tuple types inductively. So there's lots of details on this slide. I'm not going to go over it. You can look at the slide later on. But the point is that here we make an instance for show tuple over a type level list of types. But then here we use it on a real tuple type, right? This is not some HList constructor thing applied. This is just taking a normal Haskell or Mu tuple of int, string, and bool, and it still works out. It somehow still gets to this instance. Okay, we have open data kinds instead of closed data kinds. So in this example, we define a data kind here, and then separately from that, we say, oh, by the way, this type is actually one of the types that belong to this data kind. We have closed type, only closed type families, but we do have functional dependencies for them. So like in this example, like this is something you can't write in GHC currently. You know, it's the classic triangle example where any two of the arguments and the result uniquely determines the other argument. And we have partial type synonyms. So you can write a type synonym that contains a wildcard, and then at every here, and then every place where you use that type synonym, you know, we will solve by unification to figure out what the wildcard should be. Yep.
So what's the trifold column? Is it a tuple?
Oh, this here?
Yeah.
Oh, it's handily defined here so that all fits on one slide. Yeah. So this is the type constructor name that's used here. And so everything on this slide, just to motivate it somehow or somewhat, is based on the type relational algebra library that we use, where again, I can save time by just referring you to Leonard and Morton's paper from Haskell Symposium 2016. So you can see there examples. Well, I think this is actually one of the examples where we need this kind of functional dependencies to get good type inference for code that involves type relational algebra. Okay, so that's Mu. And then for Cortex, which is, you know, what we're emitting at the back end of the compiler. So the type system of Cortex is based on a small number of built-in base types, and that's all you get. You can't make any new types. So everything is either represented as an int that doesn't fit into it, so you have a purely sum type that's an int. If it's a sum of products, then it's a record, and then one of the fields is designated as the tag. Well, we have type A, which is like a runtime type tag. I've only put it here because some of the examples later on use it, so I wanted to make sure that it's not something surprising there. And then for the actual type system, so it's basically a simply typed lambda calculus with type variables, which doesn't mean anything because you could say, oh, but do I mean system F? No, I don't mean system F, because if you look at this one, there are no binders for any of these type variables. Like here or here, we just use these type variables. So I've done the disclaimer, right? That opinions, yeah, so I think this is bonkers. So what we have here is that,
I agree.
okay, so this type variable here, like morally, it's kind of scoped over by this definition, right? So you could imagine that this is for all A to int, array A to int, but then this A used here is not, right? Because it's referring to, if you fill in all the type variables consistently, that means that whenever you use this function, this local definition should get the same type as this one. But this is not apparent from anywhere in the types. Also, in Cortex, there's no parametricity, so you can write functions. Well, you can't write in Mu a function that is not parametric, but you can use functions that you would, let's say, write in C++, where you have access to type casing, and then you can write a non-parametric function. And because of this, or mostly because of this, there's explicit instantiation added in X. So here, when I pass map, map increase some access, I pass this to sum. What actually I need to do is, it's not just map. I can't just use map because map is polymorphic. I have to instantiate map to this particular type. You know, instead of A to B to array A to array B, I have to instantiate it to one where the B is int. By the way, note how I'm not saying that B is int. I'm actually giving the full type, the instantiated type, which is also quite inconvenient. So here you would have to write this. Well, right. I mean, no one's writing this, of course. It's just the compiler omitting this. But also, there's no type class polymorphism. And if you think about it, if we don't have higher rank types, and we basically just, you just put some type variables wherever and hope that it will work out. You can't really type most dictionaries anyway. So you can't just do the usual dictionary passing implementation of type classes. So you just can't. Like, by the time you've compiled your program, you have to get rid of all type class polymorphism. I like Richard's like face of disgust at this. So for the diamantic semantics of Cortex, so Cortex is strict. Let binders are strict. So what is the escape hash? Why did I say that Mu is not strict, but rather non-lazy? Well, it's because we have this byname annotation you can attach on definitions. And basically, for example, for from maybe. So if you have a definition that's marked as byname, what happens is that in Exp, one of the transformation or like lowering phases will inline your function definition and then do the beta reduction syntactically for each occurrence. But of course, this means that further upstream, you can't be allowed to, or you must make sure that your function definition is not inlined by some other optimization. And then, so when you write a module and you actually compile it, so what is the end result of that? So the modules are serialized as a value of type module, which is like a glorified record, where each field of the record corresponds to an exported definition of your like exported function from your module, and that's all, right? Because we already established that you can't make new types anyway. You can only make new terms. And one interesting aspect of this is that if each top-level definition becomes a field of the record and everything is like strict, that means if your program exports an int, but the definition of, then that int will be evaluated at compile time because you need to put the int into the record. So, and this can even mean that you can get like runtime errors during compilation. Okay, so how are we approaching using GHC to compile this language? Well, on the technical side of it, So we use GHC lib generator, which if you don't know it, it's worth looking at. So it's a library. Well, it's not really a library. It's a package that Digital Asset developed, which basically takes a GHC source tree and converts it into a standalone Cabal package. And the reason this is important for us is because we are writing a Mu compiler in Haskell. We're not writing a Mu compiler in Mu or a Haskell compiler in Haskell. Bootstrapping is completely out of the picture. And you can't import the GHC that you yourself are using to compile your compiler if you're patching that GHC so that instead of compiling Haskell, it will compile Mu. So this is super useful for that. And then we basically take the GHC libified version of a given GHC commit, put that into a Git repo as the root commit, and then apply our changes to it. But of course, we try not to apply too many changes. So it's beneficial to us if we can keep out of GHC, so there's less churn as we keep updating GHC. So we try to use the API, of course, as much as we can. Sometimes that involves, Lego instead of Duplo API usage. So there's a lot of the nice high-level does everything for you APIs that we can't use, but we do find some smaller blocks that we can. Type checker plugins. So for example, the inductive tuple instances, that's something we implemented as a type checker plugin. So basically, if you have a wanted constraint on some type class applied on a tuple, we try to solve it via the same type class applied on the inductive tuple. And of course, any changes that we think are generally useful or is a bug fix, we try to upstream. And then whatever remains, we patch GHC lib. So then whenever we need to upgrade GHC, we GHC librarize it again and then reapply all the patches, and hopefully not much gets broken. So driving GHC. So how do you have GHC do what you want it to do? So one problem for us is that GHC, of course, likes to go out to the file system and try to load source files for you, which we can't have because A, nuage, so we have this database of source code, and B, because some of the modules don't really exist. They are made up on the fly because they are just exposing non-Haskell functionality to Mu. Or sorry, non-Mu functionality to Mu. So that's a bit painful, and that's something that maybe that could be interesting to other users of the GHC API, where instead of telling GHC to do everything and go out to the file system, it would be nice if you could somehow virtualize that, if you could somehow parameterize GHC with what it means to load the source module, what it means to compile one, because some of these, the compilation pipeline is just generating code directly. And then after that, it's actually quite simple because we just run the normal GHC pipeline up to tidy core, and then we register the resulting mod details and mod interface one by one with GHC, because we have to process them one by one because we can't let GHC do everything, because then some of those are compiled differently. So it all ties together. And everything except GHC prim and RTS is ultimately provided by us. So for the type classes, well, we are doing specialization on everything. So there's this ticket for GHC where I figured that, oh, well, actually, there's no reason we shouldn't be able to specialize no inline definitions. And then turned out that I'm like the nth person to make this discovery. So this links to a long line of related previous tickets. Unfortunately, what everyone else seems to want is the ability to one by one decide that some definition, although non-inlineable, should still be specializable. Whereas for us, what we would like is just a flag that just all or nothing, that just specialize. We want you to specialize. So, and on top of specialization, so we also need to do monomorphization for the reason that the types, like the types that are only really defined in Mu, some of them are actually interesting, but we need to compile them away. So in this example, we have some type, so here we call some internal function that's not written in Mu, and we pass it this runtime type tag. And the reason we need to do that is because this implementation is potentially non-parametric, and it actually isn't parametric. And so it needs to know the type, and that's fine. But of course, in Mu, you can add the phantom type parameter to track that type to make sure that you will pass the right type tag, right? But because basically what you want here is that even though this thing is untyped, but you always want to put things of the same type into it. So you can add the nice typed API to it, but the problem is that if this new type, right, if you rewrite everything by this new type, which is pretty much what you have to do if your compilation target doesn't support any custom types. So if this whole thing is represented by this opaque object, then here, when we get here, how do we know what this type should be? And if we just try to do this, I think GHC ends up feeding us an any, the capital A any type. But even if it didn't, if you use this in different places at different times, we want to be able to generate different versions of this code. So for this, we basically just do a whole program monomorphization step after we get the core from GHC. But of course, that means that's whole program, so that sucks. Well, the good news, I guess, is that we do get something for free from it as well, because we get tree shaking. But how do you do separate compilation? So we don't know yet exactly, but what we do know is that there is some level of separate compilation that you can get for free from GHC, which is to compile up to core, and then only do the whole program stuff by loading your previously compiled core. So actually, one thing about this that I'm not sure I understand why is it that we have to call prep on all these loaded cores. So GHC doesn't really support saving prepped core. It's only tidy core that you can put into or next to an interface file. All right, because what we use is the interface file plus all the core serialized. So this is not so nice, because this is a per module processing that we still need to do every time we load the precompiled modules. So what are the internal GHC patches that we have that, oh, I didn't see the 5-minute. Okay, so let me just rush ahead in that case, because I think this is so what are the lessons that we learned from this? So on the technical side, I think the project is successful so far. Like I said, we can compile non-trivial programs. There are some situations where there's like this big change, like this big watershed change inside GHC that's painful to adapt to. The multiple home units migration was one where suddenly nothing worked and we couldn't compile anything. We couldn't compile our compiler, and for deep reasons it turned out. But then it turned into a huge win by the time we were finished with it, because the reason we couldn't compile our compiler anymore was because it was doing all kinds of evil hacks that were not needed now that we have multiple home unit support. So that's cool. The inversion of control to feed files and resolve dependencies, like I mentioned, I found out that there are some other GHC developers who are interested in this. It's hard to get a good grasp on what exactly the general solution to this would be, but I would love to talk to people who are interested in this. Okay, this is not so interesting. Okay, and other lessons. So GHC is very easy to reach out to, and easy to find people who are happy to try to help. So that's great. On the other hand, I wish there was some place that is more appropriate for the kind of questions and problems that we bump into, because on the mailing list there doesn't seem to be a good appetite for like open-ended ideation or discussion on, how would I approach this kind of problem, and you get funneled to the bug tracker. But I don't think that, I don't know how to do this. I think that's a poor bug ticket, but that's where the funnel goes. So that's something I wish we would have. The comments and especially the notes are super useful in understanding locally how and why something is. But there's no big picture, how it all fits together information on the API usage. And I think that Simon mentioned this, or someone mentioned it in Simon's presentation before, that I'm not even sure, and I think no one really knows what even the GHC API is. Is it all the Is it all the modules? Is it the 700 plus modules that you get in GHC lib? Is it only what the GHC, top level GHC module re-exports? I don't know. But at least so far we haven't really needed to export private functions. So at least what is there seems to have been enough for our needs. And I guess I'm out of time anyway. So thank you. And I'm open, of course, to questions. Yep. And you can read the skipped